Welcome back. In this session, we will implement differential evolution on MATLAB. Before trying to implement, let us just quickly go through the pseudocode of differential evolution once again. The input to differential evolution is the fitness function, the lower bounds, the upper bounds, the population size, the number of iterations, the scaling factor and the crossover probability. So, this crossover probability will be required to decide whether to perform crossover or not. So, the first step is to initialize a random population, then we need to evaluate the fitness of the population, then we need to start the iteration loop, right. So, for each population member we are supposed to find a donor vector. So, donor vector will be found using 3 randomly selected solutions XR1, XR2 and XR3. Right. Once we have generated the donor vector using mutation, we need to perform crossover to get the trial vector. So, the elements of the trial vector will be either from the donor vector which we generated using mutation, or it will be from the target vector which is actually undergoing crossover. Once we find out this trial vector, we need to find out the trial vector for the next member, right. So, we are not supposed to update the population immediately, we need to determine all the trial vectors. That is why this for loop is separately written before we bound and evaluate the fitness. So, once we have determined the trial solutions for all the target vectors, we need to bound each of them, right, and we need to evaluate the fitness. Once we have evaluated the fitness, we need to perform a greedy selection between the trial vector 1 and the target vector 1, trial vector 2 and target vector 2, and then update the population for the subsequent generation. So, we will implement this on MATLAB, right. So, similar to what we have been doing previously, we will first walk you through the code and then we will get into the debug mode and execute it line by line, so that it gives a better understanding of the working of differential evolution. So, this is the differential evolution code. So, by now you would be knowing these 2 lines, it will help us to clear the command window and to clear the workspace. So, line 5, 6, 7 is similar to what we have been doing in particle swarm optimization, teaching learning based optimization, that we define the lower bound of the problem, we define the upper bound of the problem, and we define variable prob which is actually a function handle. So, this functional handle is going to contain the optimization problem which we are going to solve. So, in this case we have given it spear new, because spear is already a inbuilt function in MATLAB. So, we do not want to disturb that. So, what we have done is we are calculating the fitness using this spear new function. So, irrespective of the number of elements in X, each element would be squared and the sum of square of all the elements will be stored in this variable f, and this is what is being returned, right. So, this is the same function which we have been using for the other 2 meta heuristic techniques, right. So, this prob will help us to determine the fitness function value. As and when we want to determine a fitness function value, we will use this variable prob, which in turn will access this function spear new, right. So, and then we need to define the parameters related to differential evolution. So, here there are 4 parameters. One is the population size. Right now we have taken the population size to be 5, the number of iterations to be performed. So, that we have taken it to be 100, the crossover probability to be 0.8, right, and the scaling factor which will be required in mutation as 0.85. So, these are the 4 parameters that we need to define with respect to differential evolution. So, this section defines the problem definition, this section defines the values of the parameters required by the algorithm. So, this variable f we are initializing it with nan, right. So, it is supposed to contain the fitness function values of the NP population member. Similarly, we define this vector fu which will contain the fitness function value of the newly generated trial vector. So, f will contain the fitness function value of the target vector and fu will contain the fitness function value of the trial vectors, right. So, initially we assign it nan, as and when we find the fitness function we will appropriately assign those values. So, this is just pre initialization. As of now they do not contain the fitness function value, but we just create that vector with appropriate size, right. So, then to determine the number of random numbers that would be required, we need to know the number of decision variables. We get the length of lower bound, So, that will tell us the number of decision variables, and then we employ this variable u, which is supposed to contain the trial vectors, right. So, trial vectors, depending upon the size of the problem, the number of columns would vary, right. So, the number of column would be equal to the number of decision variable, and the number of decision variable is given in this D, right, and we will get as many trial vectors as the number of target vectors, and the number of target vector is given by NP, right. So, we will get here a matrix of NP cross D dimension, NP rows, D columns, all the values would be nan to begin with, right. As and when we determine the trial vector, we will save it in the corresponding row. So, this step is to generate the initial population. So, what we are doing is, we are replicating the lower bound NP times, and we are replicating the range UB minus LB provides us the range, right. So, again that we are replicating NP times, right, and then if we see this the dimension of this, it will be NP cross D, because the number of rows is governed by this NP and the number of columns is governed by the length of UB minus LB, right. So, this will be NP cross D, and we generate NP cross D random numbers between 0 to 1 and do an element wise multiplication with this range. So, this will help us to generate the initial population. So, the line 26 will help us to generate the initial population, right. So, that is similar to what we have done in teaching learning based optimization and particle sum optimization, right. Line 28 to 30 is used to determine the fitness function value of each member, right. So, we run this loop for p is equal to 1 to NP, and we access the solution pth solution. So, when we say pth solution, it is the pth row and all the columns, that is why we give this colon operator, right. So, uppercase P of p comma colon. So, the pth member in the population P will be sent to this function sphere new through this variable prob, and it will return the fitness function value, which will be stored in f of p, right. So, this loop will run NP times, and we will be able to determine the fitness of all the individual members. So, that would complete the initialization procedure. So, right now we have the initial population, the fitness function corresponding to each population member, and we have created appropriate variables for storing the trial vector and the fitness function for the trial vector, right. So, now we start this iteration loop. So, line 33 we start the iteration loop, and that will go on line 77. So, that is the iteration loop. So, anything that is contained between line 33 and 77 is going to be repeated t times, right, because t capital T is the number of iterations that we want to perform. So, in each iteration for every member we are supposed to generate a donor vector and a trial vector, right. So, that is why we have this for loop. Anything between this line 35 and this line 60 will be repeated NP times. So, basically what we are doing is, for each member we will be performing a mutation and crossover, right. So, now we need to perform mutation. So, if you remember, the equation for mutation required us to have 3 randomly selected solutions, right. So, what we can do is generate 3 random numbers, right, between 1 and NP, and we can check whether they are equal to I or not, right. Let us consider the population size to be, let us say 10, right. So, and let us say we are working with the solution 5. So, we are supposed to select 3 numbers, right, which are not identical and they are not equal to 5. So, one way to do is that to randomly select 3 numbers and check whether each of them are equal to one another or not, and also check whether it is equal to 5 or not. If it is equal, if it happens that, let us say R1 is we select to be 2, R2 to be say let us say 3, R3 to be let us say 8, right. So, we need to check whether any of this equal to 5 and all of them are unique, right. If not, we need to again go and generate random numbers. So, that way, that is one way to generate those 3 numbers, but what we will be doing over here is, if our population size is 10, right, and if we are working with let us say the 5th solution. So, what we will do is we will generate something called as candidate, right. So, the candidate now are all the solution except 5, right. So, it is 1, 2, 3, 4, 6, 7, 8, 9, 10. So, this we can generate using this command, right. Candidate is equal to, we can say 1 to I minus 1, that will help us get these values, and then I plus 1 up to NP, right. So, that will help us to generate this vector if I is equal to 5. If I happens to be 6, then the candidate vector would be 1, 2, 3, 4, 5, 7, 8, 9, 10, right. So, this way we can avoid the solution which we do not want. So, here we do not have 6. So, once we have this, right. So, what we will do with this is we will randomly permutate this. So, when we randomly permutate, let us say we get 10, 1, 9, 8, 7 and so on, right. So, once we randomly permutate this vector, these first 3 numbers would be unique, because here if you see all the numbers are unique, they do not contain the solution 5 which we need to avoid, right, and since all of them are unique, I can randomly shuffle them and take the first 3, right. So, that way we will be able to get 3 solutions which are unique and not equal to the ith solution, right. So, this is the strategy that we will employ to generate the random solution. So, this way we can always be sure that the 3 solutions which we are selecting are unique as well as they are not equal to I, and we do not need to employ if condition to check that. So, here we are selecting the candidates, right. So, candidate is I to I minus 1, right, and I plus 1 to NP. So, we have generated that vector which contains indexes of all the population, right, except for the ith member, right. So, this is the list of candidates. These are the potential candidates from which we can select the random solution, right. Remember, these are not the entire solution vector, but just their index, right. The solution vector themselves are stored in P, right. Right now we are only identifying the random solutions. So, once we have this candidates, we can use this randperm function. So, randperm function we can see over here. So, if I give randperm of let us say 10, it will permutate numbers 1 to 10. So, here if we see the numbers are between 1 to 10, right, and they are randomly arranged, right. So, if we do this, as every time we do this, we will have numbers 1 to 10 randomly permutated, right. So, this will help us to shuffle, right. So, we will use this function to shuffle, and then we require only 3 solutions. We do not require all the 10 solutions, we require only 3 solutions. So, what we will do is randperm of 10 comma 3. If we do randperm of 10 comma 3, it will give us 3 solutions, right, which are unique, right, and they are taken from 1 to 10, right. So, this is how we can use the randperm function over here. So, here we say randperm NP minus 1 comma 3. So, this 3 should be clear because we require 3 unique solutions, right. This is NP minus 1, not NP, because there are only NP minus 1 elements over here, right. So, if NP is 10, candidates will have only 9 elements, because we are eliminating the ith variable, right. So, there are only 9 variables. If NP is 10, there are only 9 variables. So, now we are accessing those particular solutions. So, when we do this candidates of randperm of NP minus 1 comma 3, it will access candidate of 5, candidate of 6 and candidate of 1. Those 3 values we are storing in this variable IDX, right. So, IDX is going to contain the 3 randomly selected solutions, and these 2 lines will ensure, right, that these 3 solutions are unique, they are not equal to one another, and that they are also not equal to the ith variable. So, this was the condition required in mutation. Remember, we require 3 random solutions, we need to select 3 random solutions, all the 3 solutions have to be unique, and on top of that they should not be equal to the target solution, right. So, target solution is indicated by I. So, it should not be I, we need 3 random solutions R1, R2, R3. These 2 lines will help us to implement that. When we run this in debug mode, it will be much more clear. So, now that we have identified the 3 random solutions, right, we extract the solution. So, we say x1, x2, x3 is equal to P of index of 1, right, because the 5th solution is in position 1. If these 3 are the selected solutions, then 5 is located at IDX of 1, 6 is located at IDX of 2 and 1 is located at IDX of 3, right. So, we use that as the row, and we need to extract all the columns, right. We need to extract this from the population vector. So, now we have selected the 3 solutions, the actual 3 solutions. IDX contained only the index of which solution is to be selected, right, whereas x1, x2, x3 actually contain the solution because we are extracting it from the corresponding row from the population, right. So, the dimension of x1, x2, x3 will be, it will be a row vector, right, and the number of columns would be equal to the number of decision variables. So, once we have identified the 3 random solutions, we can generate the donor vector. So, this is straightforward, V is equal to x1 plus f into x2 minus x3, right. F is already a parameter which is to be supplied by user. So, here we have taken f to be 0.85, right. So, this will help us to determine the donor vector. So, in order to generate the trial vector, right, the trial vector will contain the value of either the donor vector or the target vector, right. So, to do that we will require this random number r, and we also require this randomly selected number del, right. So, del is between 1 and decision variable, number of decision variables. So, it is a random integer which has to be between 1 and decision variable. So, we need to first generate del, right, and then we need to generate random number for each of the variable. In line 50 what we are doing is del is equal to randi of d comma 1. So, randi, you have seen randi, the use of randi in TLBO, right, for generating teaching factor we had used, right. So, when we say rand of d comma 1, it randomly generates one integer value from 1 to d, right, and since this is 1, it returns a scalar value, right. Since we are starting from 1, we do not need to give 1 to d, it is sufficient to give just d, right, and we require only one value. So, that is why the second one is given. So, you can quickly do this over here and see what happens. So, when we say del is equal to randi of 100 comma 1, so it will give us a random integer, right, one value which is from 1 to 100, right. So, that is how we are generating the del value, right. So, once we have generated the del value, we need to run a loop for all the decision variables. Remember that equation which we saw is for all the variables. The trial vector will have a dimension of 1 cross d, right. We just need to choose whether the jth value will come from the target vector or from the donor vector. So, we run this for loop over here for j is equal to 1 to d. We generate a random number using this function rand, right. So, we check for this condition, if rand is less than or equal to PC, right, or if it is equal to del, right, if j is equal to del. If that condition satisfied, we need to take the value of the trial vector, right, from the donor vector, right. Otherwise, we need to take the value of the trial vector from the target vector. So, target vector is stored in P, trial vector is stored in U, and our donor vector is in V, right. So, here we need to see that this is a double equal to sign, that is a conditional check, right. If either this condition is satisfied or this condition is satisfied, it will assign it from the donor vector, else it will assign it from the target vector, right. So, this for loop will run for d times because we have d decision variables, right, and this for loop is inside this external for loop for every member. So, for every member that loop will run for d times because we have d decision variable. So, that would complete the crossover operation, right. So, at the end of line 60 we would have completed for all the population member crossover as well as mutation, and the trial vectors are stored in U, the target vectors are in P. This V, if you see, we are not necessarily storing V of every population member. We generate the V for the first population member, right, I mean decide on the trial vector and then we overwrite it, because at the end of crossover we will require only the trial vector which is stored in U and the target vector which is stored in P. We do not require the individual donor vector, because greedy search we are going to perform between the target vector and the trial vector. So, we are not storing the donor vector, every time we are overwriting the donor vector, right. So, remember we are overwriting after making use of it, right. So, it is not like we are never using it. So, once the mutation and crossover is over, right, for a particular member, we need to do it for the second member, third member till the NP members, and then here we again run a loop for j is equal to 1 to NP, and then we bound the variables, right. So, this bounding of the variables we have seen previously, that if we use a min operator, min of ub comma the actual solution. So, the actual solution is jth row all columns. So, jth row all columns will give us the jth solution, right. So, we are using the min operator. So, if in line 65, if any variable in the jth row of u violates the upper bound, it will be brought back to the upper bound, right. Similarly, line 66 will ensure that the trial vector u of j comma colon, if any of those values violate the lower bound, it is brought back into the lower bound using this max operator, and if the values do not violate the lower and upper bound, it will be retained as such. So, we had seen 65 and 66 in detail when we learnt teaching learning based optimization, right. So, now this trial vector is bounded, right. So, what we will do is we will evaluate the fitness of it. To evaluate the fitness of it, we need the fitness function. That fitness function we have stored in the variable prob. So, prob is a function handle wherein we are sending the jth row of u to this prob function. We will be able to determine the fitness function of the jth trial vector, right. Once we have the fitness function of the jth trial vector, we are ready to perform a greedy selection. So, we are checking whether the fitness of the jth trial vector is better than the fitness of the jth target vector. So, if this condition is satisfied, we overwrite the jth member of the population with the jth member of the trial solution, right. And similarly, we replace the fitness function value, right. So, this is how the greedy selection is performed, right. So, since it is inside this particular for loop, right, it will be done for NP times, wherein we are comparing the first trial with first target, second trial with second target, third trial with third target, and depending upon whichever is better will be taken into the population. So, if the target is actually better, then we do not need to do anything. That is why we do not have an else part to this if loop. That particular solution will be retained, right. But if it happens that the trial vector is better, then the trial vector is used to override the jth member of the population, right. So, this will again be done for NP times because our population is NP, and this entire procedure is inside this for loop which governs the iterations, the number of iterations. So, this will be repeated for t times, right. So, that completes the implementation of differential evolution. Just like in TLBO, at the end of it we are interested in what is the best solution obtained so far, right. So, that can be determined by determining the minimum of the fitness function, right, using this min function. So, this min function will give us what is the minimum value that we are storing in this variable best fitness, and it will also give us the location as to where it is located, right. So, using this IND, which is the location of the best fitness function value, we extract the corresponding population member, right. So, let us say if IND is 5, then we are extracting the 5th row of the population and we are assigning it to best sol. So, that way we will be able to see what is the best fitness and what is the best solution at the end of t iterations, right. Let us now run this code in the debug mode, right. So, let me put a breakpoint over here, and if we execute this code, right. So, the first step is CLC. So, as you know that it will clear the screen. The second one is it will clear the workspace, right. So, the lower bounds are defined, the upper bounds are defined, and now we are defining the function handle, right. So, prob will be defined. So, now prob is a function handle. So, we are solving this objective function sphere new, right. So, now we need to define the parameters, right. So, population size is 5, number of iterations is 10. So, the crossover probability is being defined as 0.8, the scaling factor is defined as 0.85, right. So, now we are defining a variable f which will have NaN values, as many NaN values as the population size, right. So, here the population size is 5. So, we are having 5 NaN values, right. So, the next step is to find out the length of the lower bound. Length of the lower bound is 5 in this case, right, and then we generate the initial population as usual, right. So, here if we see, so this is the population, the random population which we have generated within the bounds, and this is going to be the new solutions which are generating in every iteration, right. So, as we generate solutions, we will store in this U matrix, right. So, that we had defined here, right. So, we will store that in U matrix as and when we generate. So, once the population has been defined, we need to evaluate its fitness function, right. So, we are running this loop from 1 to NP. So, now it will go into the fitness function. So, again same thing, x is now the first row, as you can see the first row is 5.429 and these values. So, those values would be over here. So, it will determine the fitness function value and that is being returned back, right. So, here if we see the fitness function of the first solution has been determined to be 129.0137. So, similarly, if we keep doing this, right. So, it will determine the fitness function of all the 5 solutions. So, now we have the initial population generated in this line 26 and we have evaluated the fitness function value over here, right. So, now we have done that, we can begin the iteration loop of differential evolution, right. So, if we step in, so t is 1, I is also 1. So, now we will determine who are the possible candidates who can be partner in the mutation phase, right. So, we are creating this vector 1 to I minus 1. So, in this case it will be 1 to 0. So, that will not return us any value and this will be 2 to NP, right. So, if we do this step, so here if we see candidates are 2, 3, 4, 5. Now, we have eliminated the ith solution from the list of candidate solution, right. So, because for the first solution it cannot be partner. So, we are going to select partner from this 4 solutions 2, 3, 4, 5. Now, what we are doing is a permutation random from 1 to 4. So, this will be 4 NP minus 1, this value would be 4 and we are taking 3 randomly permutated values. So, here in this case 4, 3, 5. So, now if you see this satisfies our purpose that we are able to select 3 different partners which are not equal to the ith solution. So, in line 41, 42, 43 we are just going to assign the corresponding solution to x1, x2, x3, right. So, P if we see this is the original population, IDX is 4, 3, 5. So, IDX of 1 is 4. So, x1 will be the 4th solution, right. So, let us just see that. So, x1 is this one, right, and if we look at the population, the 4th solution is 9.3195, 0.3647 and so on. So, that is the first solution, right. So, if we continue this, the second solution, the second partner solution is IDX of 2, right. So, IDX is 435. So, IDX of 2 is 3. So, the third solution is nothing but x2. So, the third solution is this one and which is assigned as x2, right. So, similarly, the third solution x3 is determined. Now, we have figured out solution x1, x2, x3, right. We need to calculate the donor vector. So, donor vector, this is the equation that was given in our discussion, right. So, x1 plus f into x2 minus x3. So, if we do this, then this is the donor vector. Remember, the donor vector may or may not be in the bounds, right. So, in this case it is not in the bounds, our upper bound is 10, right. So, in this case the donor vector first variable, fourth variable and fifth variable are not in the bounds, but we will not be bounding them, right. So, now we need to perform the crossover for the first solution itself. For performing crossover, we need to first randomly select one of the decision variables, right. So, that is what we are doing with this randi, right. So, randi of d comma 1 will give us a scalar value from 1 to capital D, D in this case is 5. So, 1 to 5 it will give us one random value. So, in this case it happens to be 4. So, this value is randomly selected, right. Now, we need to perform the crossover operation with these two conditions. So, if we need to select a random number if it is less than the crossover probability, or if del is equal to j, we need to copy from the donor vector, else we need to copy from the trial vector. So, the trial vector is going to be stored in U. For j is equal to 1, the value of j is 1 now, right. So, it goes into this, this condition is satisfied. So, the random number that it generated was less than crossover probability, because del is 4 and j is 1. So, this condition was not satisfied, this condition was satisfied. because as soon as we say rand, we get a random number. So, here we did not save it in a particular variable, otherwise we could have seen what is the actual value. So, now u, if we see, it is copied from the donor vector. The first value of donor vector is copied as the first value of trial vector, right. So, similarly we need to proceed for the second variable. So, for the second variable, if we see, again that condition is satisfied. So, 4.9037 has to be copied over here, right. So, if we continue that, so that happens, right. For the third solution, the condition is again satisfied, right. So, 4.8190, which is from the donor vector, is copied over here, right. And similarly, for the fourth time, again that condition is satisfied, right. For the fifth time, again the condition is satisfied, right. So, in this case it happens that all the 5 values came from the donor vector. So, our donor vector was this thing 12.505, 4.9037, 4.819, minus 1.3556 and 13.1750, and that has been copied over here. So, in this case no value from the target vector has come, but that need not be always true, right. So, depending upon the random number we generate and the random decision variable that we select over here in line 50, it may happen that some of the values are being copied from the trial vector also. Remember, we are not going to bound this solution, evaluate the objective function or update the population, right. So, we need to complete the mutation and crossover for all the solutions, only then we will bound and do greedy selection, right. So, this end will make sure that we are going back to this second member. So, if we go to this, so now if we see, I will have a value of 2. So, similarly the candidates are except 2, 1, 3, 4, 5. We need to select 3 candidates from here 1, 3, 4, 5. So, we randomly permutate values 1 to 4 and select 3 values and then extract 3 values from here, right. So, in this case the solution 413 are the partner for the ith solution. Ith solution is currently the second solution. So, the partner for the second solution are fourth solution, first solution and third solution. So, line 41, 42, 43 again will be just assigning those solutions from the population to x1, x2, x3, right. So, these are the 3 solutions x1, x2 and x3. Again we need to calculate the donor vector, right. So, this is the donor vector, again donor vector is not within the bounds. So, we need not worry about the bounding of the solution over here. So, in crossover we require a random decision variable. So, we select that, right. So, in this case the decision variable is 3, right. So, here if we see even in this case the random number generated was less than crossover probability, right. So, again in the second case 2, the third case 2, the fourth case. So, this is the first time if you see it is coming to this else part, right. So, now the donor vector was over here 9.49, minus 1.17, 5.01, 5.17 and 2.52. So, the first 3 values were copied. For the fourth value, since neither of this condition is satisfied, we will have to take the value from the population, right. So, population if we see, we are currently in the second solution and j is 4, right. So, second row fourth column if you see, it is 6.4134, that will be coming over here, right. So, step in, right. So, as expected 6.4134 comes over here, right. Continuing that for the next variable, right. So, it comes from the donor vector, right. So, now we have generated 2 trial vectors, right. So, similarly you can debug and look for all the other trial vectors. What we will do is, we will have a breakpoint over here and we will click on this continue, right. So, now all the 5 trial vectors are generated, right. So, since it is similar, we did not go through each and every solution. So, we had seen both the cases wherein it goes into this if condition. So, now that we have generated all the trial vectors, we will be checking whether they are in the bounds. If whichever value is not in the bounds, we will be bringing it either to its lower bound or the upper bound, right, and then evaluate its fitness. and perform a greedy selection strategy, right. So, this loop also runs from for j is equal to 1 to np. Remember, we are still in the first iteration. So, if we type t over here, it is still the first iteration, right. So, if we do this step, right. So, the first variable, right. So, ub, right. So, ub is 10 10 10 10, right. So, it is all these 5 values are going to be compared with 10, wherever 10 is being violated. So, for example, in the over here the first variable and the last variable, right. So, those two are violating the upper bound. So, they will be reset to 10. The value of the first and last variable have been reset, right. Similarly, this variable, if we see, is violating the lower bound. The lower bound is 0. So, since this variable is violating the lower bound, it will be reset to 0. Yes. So, now this first solution is within the bounds. So, since the first solution is within the bounds, we can calculate its fitness function and perform a greedy selection, right. So, in this step, if you see line 68 over here, it will we are calling this variable prop. This prop is nothing but the function handle sphere new. So, if we do step in, it is going to this function, right, and again the fitness function will be evaluated. So, as we can see, the first row of u has been sent into the function as input, right. So, the fitness function is calculated, right. So, now the fitness function value is 247, right. So, if we look at fu, the first value is 247 and the solution which are already there, right, that fitness is 129. So, this condition is not satisfied, right. Right now, we are looking at j is equal to 1. So, fu of 1 is not less than f of 1. So, this part will not be executed, right, and the population remains the same, right. So, this solution is now discarded. So, if we continue this for the second solution, again this is the only variable which is violating the bounds, right. So, this will become 0 once line 65 and 66 are executed, right. So, this is 0, right. Again the fitness function will be evaluated with this fu, right. So, in this case the second value is 162.8262 and over here it is 115, right. So, even in this case the newly generated trial vector is not better than the second solution. So, in the third case over here, if we see this variable is violating, this variable is violating, both of them are violating the lower bounds, right. So, both of them have been reset to 0, right, again calculating its fitness function value. So, the fitness function value would be 23.3707. So, the third fitness function is 144. The current third solution in the population has a fitness of 144, whereas the newly generated trial vector has a fitness of 23.37. So, the newly generated solution will be taken into the population, right. So, we are overwriting the jth row with the third row of u, right. So, u contains the trial vectors. So, both the population as well as the fitness function have to be updated, right. So, that is what we are doing in line 71 and 72, right, and then we need to continue this for the fourth solution. So, for the fourth solution, right. So, fourth solution, if we see, the third and the fourth variable are violating the lower bounds, right. So, those are set to zeros. Again we evaluate the fitness function, right. Even in this case the newly generated solution, fourth solution, has a fitness function of 48, whereas the original one has 136, right. So, that is why we override this, right. And finally, the fifth solution similarly, right. So, for the fifth solution the fitness function of the trial vector is 166, whereas the original solution which we have is 19.3. So, we do not need to overwrite. So, if we step this, right. So, this completes one iteration of differential evolution, right. So, similarly we will have to perform all the iterations, the second iteration, the third iteration, all the way up to 100 iterations, because in this case we had set the value of t to be 100, right. So, as you can see, the implementation of differential evolution is very easy, right. So, let me just execute this, right. Let me put a breakpoint over here. As soon as it completes all the iterations, I want it to pause So, now I can give this continue. Right. Let me remove this breakpoint. Right. So, now I am not interested in doing every iteration, right, because we have seen what is happening in every iteration. So, let me just do this continue. Now, let me just clear the screen. Right. Let us see our f, right, and p. Right. So, all the solutions are zeros, right. If you see, all the 5 solutions are 0 0 0 and the fitness function is 0 0 0, which is the globally optimal solution for this function, right. So, now what we are doing is similar to what we have done in TLBO and PSO. We want to determine what is the best fitness function value and what is the best solution. So, we find this min of f, right, because f contains the fitness function value. We find the minimum value is stored in this best fit and its location is stored in IND, right, and then we are extracting the population member corresponding to IND, right. So, if it happens that the second solution is the best one, then we are extracting the second solution, second row, all the columns from the variable p or the population and storing it as best sol, right. So, at the end of it, it gives what is the best fitness function value and the best solution, right. So, now let me remove all the breakpoints, right, and put a semicolon. So, now we can change this lower and upper bound and see how it is performing. So, what we will do is we will say that the lower bound is minus 100, right, ones of 1 comma, let us say I have 50 variables, right. So, 1 row 50 columns, lower bound will give 50 times minus 100, right. So, same thing I can copy it over here and let us say the upper bound is 100. Right, we are not changing the objective function, just we are changing the lower and upper bound, right. So, as you know, these problems are scalable. So, we just want to test that if the problem size is really big, like instead of 5 variables, let us say if it is 50 variables and we are working with a population size of 50 and 100 iterations. So, let us see whether it is able to find the globally optimal solution. In this case, it is able to find a solution which has a fitness function value of 9.07 into 10 power 4 and all the variables, if you see, it is between minus 100 and plus 100, right. So, the bounds are no longer 0 to 10, right. So, the bounds are between minus 100 to 100. So, this minus 67.9827 minus 63.1130, all those are within bounds, right. So, in this case we see that it is not able to find the optimal solution. So, the optimal solution was again zeros, right. So, if we take all the 50 variable to be 0, we will get a fitness function value of 0. That is the end of this session. In the next session, we will look at genetic algorithms. First, we will look into binary coded genetic algorithm, then we will look into real coded genetic algorithm, and then we will only implement a real coded genetic algorithm on MATLAB. Thank you.